For our next trick, we're going to set up a binary counter and keep using the external timer for our clock. Normally, you'll use the onboard clock, which on this PIC runs at 16 megahertz. That's 16 million clock pulses per second. Obviously, you wouldn't see any flashing LEDs. They'd be flashing on and off so fast, it would just appear as though the LEDs were just constantly on. But you can see some scenarios where you specifically want to run the processor at ridiculously low speeds. And you can do that with an external clock like we're doing here. So a binary counter is just 4 LEDs showing a binary number, and it simply counts up. So we're going to wire the LEDs on the output of port C again. To make these things simple, we'll use the least significant nibble, bits 0 through 3. A single current limiting resistor is all that's needed for all 4 LEDs. The code is in the download section again, so you can just copy and paste the code into your project again. Or you can do one of two things. The setup is going to be identical, so if you want, you can just take your Blinker project and replace the assembly code with the new code, or you can build another project from scratch. I'll just do that just to walk you through it so you don't miss anything. You'll wind up doing this eventually anyway, so might as well get in the habit. Open up MP Lab and select New Project, Microchip Embedded Standalone Project. Find your PIC, the PIC 16F. 1455. No debug headers required. We're going to use the Picket 3 and use MP assembler. Give it a name you like. I'll call mine binary underscore counter. And make sure you set it as the main project. When you get the project created and opened, you're going to right click on the, you're going to right click on the source files and create a new assembly file.asm and give it a name if you want, binary underscore counter. Then right click on the project name, select properties, then click on Picket 3, select program options from the option categories drop-down menu, and check enable low voltage programming. Maybe I should make a checklist for you guys. Then select power options from the categories drop-down menu. Make sure the power target circuit from Picket 3 is checked and the voltage level set to 4.5 or whatever worked for you previously. In my case, 4.5 volts. Click on MP Assembler Global Options and check the Build in Absolute Mode checkbox. Click OK. So copy the code and paste it into the assembler window, and we'll take a look at the code. The setup is exactly the same as before, so I won't explain that part. But we get introduced to some new instructions. Now, after setting up the tri-state register, tri-state C register as all outputs, we set the bank for LATC, because that's all we're going to use now, even though the LATC register should be all zeros because we just turned the chip on, I cleared the LATC register just to be sure. So we set up a loop, and we even used the same label as we did in the last program. But here's our first new instruction, INCF, which is increment a file. Whenever they talk about files in the PICs, they're always talking about a register. So we want to increment the register. The next part tells the PIC what register to increment. In this case, the LATC register. So it grabs whatever number's in that register and adds a 1 to it. So now every time it sees this instruction, it counts up on the register, which outputs on our LEDs. The next line is a check statement. It checks something and then takes action if the stipulations are met. In this case, BTFSC, bit test on a file, skip if clear. So you issue the instruction, then a space, then the register you want to test, then a comma, then a space, and then the specific bit in that register that you want to check. So in this case, I want to test bit 4 in the latch C register. If bit 4 is clear or a 0, the PIC will skip the next instruction in the program. It will skip over this instruction and go straight to the go to command and go back to the loop and increment the latch C register again. So as our program is running, latch C is counting up. Once the count hits 16, decimal 16, the lower nibble, which we were outputting on our LEDs, clears and bit 4 goes high. So what we're checking here is if bit 4 goes high. Then we want to clear latch C to zeros and start the count over again from 0. So that's exactly what this instruction does. It checks bit 4 and will skip over this next instruction unless bit 4 is high. So let's say we've been counting for a while and we hit 16. Bit 4 now goes high. We run our bit test, so now it does not skip the next instruction. What's the next instruction? It clears the latch register. It sets everything back to zeros, then loops back to the beginning, and starts counting up again from 0. All right, so fire up your PIC, flash the memory, and run it. So here it is in action. Count with me in binary. This LED is the least significant bit. This one is the most significant bit. So the decimal values of each bit are 1, 2, 4, and 8. So now let's count up when it gets to 0 here. So there's 15. Now when it hits 16, it starts at 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, the count would be proud. 13, 14, 15, 16, oops, it just reset back to 0. So it now starts its count over again from 0, counting up. Okay, so build it up, flash the PIC with your new program, and we'll make use of this binary counter in the next lesson.